Hello everyone, this is Professor Ng Ji Kun from UNIMAS. In this video, I'm going to give you a lecture on reinforced concrete design on the topic of durability requirement. A structural element has to have enough durability during its service life. The durability includes the resistance to exposure condition and fire protection. So first, we look at concrete cover requirement to satisfy these conditions. So concrete cover is provided to the steel reinforcement to prevent corrosion and protect it in the event of fire. The cover must be provided in such that it allows the steel reinforcement to develop good bond with the concrete. Eurocode 2 specifies the nominal cover as follows, which is C norm is equals to C min plus delta C deviation. So C min is minimum cover set to satisfy bond requirement, exposure condition and fire protection, and then delta C deviation is allowance for construction inaccuracy and should be taken as 10 mm unless where an approved quality control system on cover is specified, in which case it can be reduced to 5 mm. The minimum cover for bond is denoted as C min B in accordance with table 4.2 of Eurocode 2. For separated bars, C min B is equals to the diameter of bar. For bundled bars, C min B is equivalent diameter in accordance with section 8.9.1 of Eurocode 2. So separated bars in a cross section is that all the bars are separated. Okay, bundled bars is when you have bars in bundle like this. Okay, so here you have 8 bars, but you have only 2 bars in one bundle. So in this bundle there are 2 bars. The number of bars in the bundle is 2. Then the minimum cover for exposure condition is denoted as C min DUR in accordance with the exposure class and structural class in table 4.1 and table 4.3n of Eurocode 2 respectively. The recommended structural class or design working life of 50 years is S4 for the indicative concrete strength given in Annex E of Eurocode 2. The value of C min DUR is then determined from table 4.4n with the corresponding exposure and structural class. The minimum cover for fire protection is mentioned in Eurocode 2, Part 1-2. Rather than specifying the minimum cover, the normal axis distance A is specified. The axis distance is the distance from the center of the main reinforcing bar to the surface of the member as illustrated in figure 3.15. So therefore, A need to be equal or smaller than C nominal plus the length diameter plus the main bar diameter over 2 as illustrated in figure 3.14 and figure 3.15. So the permissible combination of member dimension and axis distance are given in table 5.5 and 5.6 of Eurocode 2 part 1-2. So just now we have seen that the nominal cover C norm and C norm here, they have to cover until the length that has to be protected also. Okay, other than the main bars, okay, as what we have seen in this cross section here, there is still length diameter that we need to provide cover to the links as well. Next, we will look at an example on determination of concrete cover. So let's say we have an interior beam of a building with moderate air humidity is going to be designed. The member size and concrete cover needs to be determined for the design calculation. The building is to be designed for fire resistance of 1.5 hours. For a preliminary calculation, the beam may be assumed as simply supported. The main reinforcing bar diameter and link diameter can be assumed as 20 mm and 8 mm respectively. The main reinforcing bars may be assumed to be separated. The design working life of the structure is 50 years. There is no description on quality control of construction. Therefore, delta C deviation is equals to 10 mm. So we cannot reduce it to 5 mm in this case, because there is no mention on quality control of the construction process. So from table 4.1 here, exposure class related to environmental conditions in accordance with EN 206-1 or MSEN 1992-1-1, which is Eurocode 2. The concrete member that is described in the example is concrete that is inside a building with moderate or high air humidity. So in this case, we can take the exposure class or description of the environment as XC3 with moderate humidity. So the exposure class is XC3. And then from table E1N or table F1 in your design guidebook, the indicative strength class for XC3 is C30/37. So this means that the minimum concrete strength class that you can use to design this structural element is grade C30/37. So the indicative strength class is C30/37. So meaning that the minimum concrete strength is class C30/37 for the structural element to be classified as structural class S4. So this S4 is very important. So when you use the minimum concrete strength class for the exposure class, then we can classify the structure as structural class S4. If we are using a lower concrete strength class, then it's not able to classify the structural class of the structural element that we are designing. So hence we are going to specify the concrete strength class C30/37 for the design of this beam. That is the minimum that you can use. Okay, and then we go to table 4.3N and look at the strength and look at the exposure class XC3, and then we go through the row here one by one. Okay, so are you designing the structural element for design working life of 100 years? No, we are designing for only 50 years. So if not, then there is no increase or decrease on the structural class. So the structural class still remains as structural class S4 after considering the first row there. And then we look at the second row here, okay, whether we are using concrete strength class of C35 or more. So no, we are not using concrete strength more than C35. So the structural class is still S4. There is no increase or decrease. Okay. If this is true, okay, you are using a higher strength class of C35 or more, then you can reduce the structural class by 1. Okay, so if you reduce structural class by 1 here, then S4 becomes S3. Okay, but it's not happening in our case, right? Then we move on to the next row is, are you designing a member with slab geometry? So we are designing a beam, so we are not designing a slab, so we don't reduce the strength class. So strength class is still S4. Okay, and then we look at the last row here, is that it's special quality control of the concrete production ensured. So there is no mention in the construction process there. So we do not reduce the structural class by 1. So the structure class is still S4. So from the first row until the last row, we see that there is no change in the structure class. So the structure class is still S4. So we can say that there is no increase or reduction in structure class for this beam. So the structure class remains as S4. And then according to table 4.2 of Eurocode 2 for separated bars, the bond requirement is diameter of bar. So C min B is equals to diameter of bar, which is 20 mm, as we said we assume using 20 mm bars in the design. And then according to table 4.4n of Eurocode 2, the minimum cover for exposure class XC3 and structure class S4 is C min DUR. For exposure class XC3 and structure class S4 is 25 mm. So C min DUR for this design is 25 mm. So to satisfy both the bond and exposure requirements, okay, the C minimum is 25 mm because we cannot use 20 mm because 20 mm will only satisfy bond, okay. And then for exposure we need 25 mm, so that we use 25 mm to satisfy both bond and exposure requirements, okay. So the C nominal is the C min plus 10 mm, which is delta C deviation. So in total we need a nominal cover of 35 mm. For fire resistance of 90 minutes for a simply supported beam, table 5.5 of Eurocode 2 part 1-2 specifies that the combination of minimum beam dimension of 150 mm and axis distance of 55 mm is possible. So from table 5.5 here, for 90 minutes of fire resistance R90, okay, so the combination of B minimum and axis distance are given in this row here, okay. So if we use minimum dimension of 150 mm, then the axis distance is 55 mm. If we use 200 mm beam, then we can reduce the axis distance to 45. So in this particular example, we are using this group of numbers. So minimum beam dimension is 150 mm, and then the axis distance is 55 mm, as in accordance with table 5.5 here. So this table 5.5 is in part 1-2. Okay, please don't refer to part 1-1 table 5.5. It's a different table. Okay, so this is part 1-2 of Eurocode 2. So in that case, another 10 mm is added to the axis distance for the corner bar with single layer of reinforcement. You have this situation, then we have to add another 10 mm for the corner bars of a single layer of reinforcement. Therefore, the beam width can be specified as 150 mm because we're using B minimum of 150 mm. And then from equation 3.38, okay, the axis distance A has to be smaller or at least equals to C nominal plus the link diameter plus the main bar diameter divided by 2. So C nominal has to be at least 47 mm. So in this case, from C min for bond and C min for durability, we get C nominal as 25 mm. But for fire protection, we need at least 47 mm. So meaning that the minimum cover is governed by 47 mm to satisfy all conditions or all requirements, right? And then we have another requirement for minimum distance between bars. So meaning that we have to specify the minimum distance between the bars that you provide. So this is what we call as the minimum distance between bars. So the minimum distance between bars is to permit concrete flow around reinforcement during construction and to ensure that concrete can be compacted satisfactorily for the development of adequate bond. The clear distance between bars should not be less than the maximum of number 1, the largest bar size, number 2, the largest aggregate size plus 5 mm, or number 3, 20 mm as specified in section 8.2 of Eurocode 2 and the Malaysia National Annex. So for example, if we are using 25 mm bars, okay, then the clear distance between bars should not be less than 25 mm. So meaning that this distance cannot be less than 25 mm. And then if we are using maximum aggregate size of 20 mm, okay, so 20 plus another 5 mm will be 25 mm to satisfy this condition. So minimum distance between bars is still 25 mm as according with number 2. And then number 3 is just 20 mm. So 20 mm is less than both of the 25 mm. So the minimum distance between bars in this particular example is 25 mm. Next, we want to look at Anchorage of Bars. But for Anchorage of Bars, I won't go through the theory review. What I want to show you is just this table 3.1 here, where we have typical values of anchorage and lap lengths as a multiple of bar size. Okay, so for different grade of concrete, we have the anchorage length and lap length, okay, for good or poor bond condition. Okay, so when you design a structure, you have to assume whether you are going to get a good bond or poor bond. If you don't know, then you may just take the average value. Okay, so anchorage length meaning that if you have a beam like this, okay, and you have a steel reinforcement inside the beam, okay, so the anchorage length means the length that you need to provide in order for the concrete to provide enough grip on the steel. Okay, and then for lap length is when you have a beam, but the reinforcement, one reinforcement is not long enough, and then you have to join the reinforcement. Okay, so this will be the length that you need to provide in order to lap the reinforcement. Next, we would like to look at curtailment of reinforcement. So it is a common practice to cut off bars where they are not required to resist moment. Each curtailed bar should extend a full anchorage length beyond the point at which it is no longer needed. So in a continuous beam, you see that the bending moment diagram will look like this. Okay, so this is what we call as the bending moment envelope that we see in the design of beams. Okay, so we have maximum moment over here, which is positive bending moment, and then we have maximum negative moment over there. Okay, other parts of the beam, they have smaller moments, so we don't need the maximum steel area that you design for this location or this location in all of the beam. Okay, so in this case we can curtail off some of the steel reinforcement in order to achieve economical design and also to prevent congestion of reinforcement at the joints. So for curtailment or reinforcement, we use the simplified rules. Okay, so if you are designing a simply supported beam like this, okay, then we have bending moment diagram which looks like something like this, okay, with maximum moment at the midspan there. So this is the maximum positive moment that we have. So we design for this maximum moment to provide these steel bars there. Okay, so 100% of the steel bar is to resist this maximum moment. And then on the other parts of the beam where the moments are smaller, we can use less reinforcement. Okay, so we don't calculate the location where the moment is corresponding to the less steel that we need to provide, but we just use the simplified rules by measuring 0.08 L distance from the center of the support, okay, and then we can cut off half of the steel to go into the connection there, okay. And then if you have a continuous beam like this, okay, then the bending moment diagram will look like this, okay, where we have maximum positive moment here, and then we have maximum negative moment there. Okay, so we design to this moment and provide this much of reinforcing steel, and then we design to this bending moment and provide this steel there. Okay, so anywhere outside of the maximum moment area we have less bending moment. So for less bending moment we need less steel. So we just use simplified rules by stating 0.15 L plus A1. So I will explain what A1 is later. So in this region here you can reduce the steel bars to only 60% of what you provide over there. Okay, and then beyond 0.3 L plus A1 you can provide only 35% of what you need over there for the maximum negative moment. Okay, as for the maximum positive bending moment, anywhere near the support of 0.3 L minus A1 we can reduce the steel to only 30% of what you need over there. Okay, same as for this support over here, we can reduce the steel amount to be only 30% of what you have for the maximum positive moment. So just now we mentioned about A1. So A1 is the distance to allow for tensile force due to shear force, which is jack cotangent theta over 2. So we will learn this in shear later. It can be conservatively taken as 1.125D. So this is for simplification. Okay, where D is the effective depth of the tension steel. Next, we want to look at serviceability requirements of reinforced concrete beams. So the two common serviceability requirements of reinforced concrete elements are deflection and cracking. So excessive deflection and cracking are not desirable in a structure. So for deflection, there are two ways of controlling deflection. So we will only be using the first method, which is limiting span to depth ratio, which is also called the dim to satisfy condition as described in section 7.4.2 of Eurocode 2. So in this course, we will only consider the dim to satisfy condition. So therefore, the limiting span to depth ratio is given by these two equations here, depending on the values of rho and rho 0. Okay, so rho 0 is the reference reinforcement ratio taken as square root of concrete characteristic strength multiplied by 10 to the power of minus 3. And then the value of rho is the required tension reinforcement or as required over BD. Okay, and then the value of rho prime in this equation here is the required compression reinforcement, which is equals to as required prime over BD. Okay, so the value of the basic span to depth ratio is to be modified in particular cases as follows. So if you are designing a flange section with the flange width to web ratio exceeding 3, so meaning that if you have a T section like this and your B and BW ratio is more than 3, then the value should be multiplied by 0.8. So you have to multiply this by 0.8 or multiply this by 0.8. Secondly, for beam and slab other than flat slab with span exceeding 7 meter with support partitions liable to be damaged by excessive deflection, the value should be multiplied by 7 over span. So if you are designing a beam with span of 8 meters, let's say, so you have to multiply this by 7 over 8 or multiply this by 7 over 8. Okay. And then thirdly, where more tension reinforcement is provided, as provided, than that calculated, which is as required, then we multiply this value by as provided over as required, but as provided over as required cannot be more than 1.5. So meaning that we can multiply this value by as provided divided by as required. Same as for this value, if this condition is the condition. And then for cracking, only the control of cracking without direct calculation in accordance with section 7.3.3 of Eurocode 2 will be discussed here. Fractional cracking is generally controlled by providing a minimum area of tension reinforcement and limiting the bar spacing or the bar sizes. The recommended values for maximum crack width Wmax is given in table 7.1n of Eurocode 2. The maximum bar spacing for crack control is given in table 7.3n of Eurocode 2. The maximum bar spacing depends on the stress in the reinforcement, which should be taken as the stress under the action of the quasi-permanent loadings. So the quasi-permanent loading is taken as the permanent action GK plus a proportion of the variable action QK depending on the type of structure. The calculation of stress level Fs can be complicated, and an acceptable approximation for office and domestic situation is to be taken as equation 3.43 here, where we assume 30% of the variable action is permanent, so that the quasi-permanent load is GK plus 0.3 QK. So this is the equation that we use for the calculation of steel stress at serviceability limit state with regards to cracking. Okay, we ignore 1 over delta here because we don't do any moment redistribution. So ignore this term here. Okay. So the maximum bar size for crack control is given in table 7.2 of Eurocode 2. That's all for the lecture in this video. Thank you very much for listening.